On a frigid night in 1943, Nazi scientists recovered a piece of copper no larger than a coffee mug, only to realize their entire war was based on impossible physics. In the Telefunken Research Laboratories in Berlin, on February 3, 1943, Professor Leo Brandt carefully lifted the copper cylinder. The device, barely 3 kilograms and no larger than a coffee mug, represented what would become known as the most significant intelligence failure in Nazi radar development. It directly contradicted every calculation German physicists had made regarding microwave technology, particularly its power output at 3 gigahertz. Just 24 hours earlier, Luftwaffe night fighters had shot down an RAF Stirling bomber near Rotterdam. The aircraft, part of the Pathfinder force, carried equipment so secret it was fitted with self-destruct charges designed to obliterate the technology upon enemy capture. Those charges had failed. The German recovery teams found the radar system largely intact, its copper magnetron still warm from operation. What German scientists discovered when they examined this captured component, officially designated CV64, exposed a technological chasm so profound it forced the German High Command to confront an uncomfortable reality. The Allies were operating in an entirely different realm of physics. The root of this technological deficit was not a lack of scientific talent, but a single administrative decision made years earlier. Following the swift victory over France in 1940, a surge of overconfidence led Adolf Hitler to issue a decree. No scientific research project could receive priority funding unless it promised definitive military results by 1942. This single directive effectively killed German long-term radar research, precisely as British scientists were making the breakthroughs that would change the nature of electronic warfare forever. German scientists already understood the theory of cavity magnetrons. Hans Holman, a German physicist, had even filed a patent for a multi-cavity design years before the British work. The problem lay in practical implementation, especially at high power levels and stable frequencies. German calculations, consistently validated by early, low-power prototypes, suggested that magnetrons operating above 1 gigahertz would be fundamentally unstable and useless for precision radar. Consequently, German radar development committed entirely to lower, established frequencies. By 1942, German systems like the Würzburg tracking radar and the Freya early warning radar operated mainly between 90 and 600 megahertz. These systems worked well, but they required immense antenna arrays, measured in meters, and provided resolution measured in hundreds of meters. The Würzburg Reis, Germany's largest operational radar, used a massive 7.4-meter parabolic dish. Together, the Freya and Würzburg systems formed the Himmelbett line, which had inflicted substantial losses on RAF Bomber Command through 1941 and 1942. German confidence in their established radar network was justified. They had deployed effective, reliable systems using sound engineering principles. What they didn't know was that British scientists had already transcended the limitations German theory had declared absolute. Erosion of German confidence began in late 1942. RAF bombers seemed to navigate with unnerving precision through total cloud cover and darkness, finding targets with an accuracy that defied conventional navigation methods. German signals intelligence detected unusual radio emissions from the bombers, brief, pulsed transmissions at frequencies around 3 gigahertz. German radio engineers, relying on their theoretical framework, initially dismissed these intercepts, insisting that generating useful power at such high frequencies was physically impossible. They believed the signals must be a decoy or a navigational beacon, certainly not an operational radar. The truth arrived on January 30, 1943, when RAF Bomber Command conducted its first operational mission using the new H-2S ground mapping radar. This centrimetric radar allowed pathfinders to mark targets in Hamburg in complete darkness and heavy cloud cover using only electronic navigation. 4 days later, the technological revelation arrived in the field near Rotterdam when the Stirling bomber was shot down by a night fighter. The aircraft, short Stirling Mark I R9264, crashed, but the H-2S transmitter survived. Inside, recovery personnel found the copper magnetron, machined with extraordinary precision, containing 8 symmetrical cavities. It was a sealed unit, entirely self-contained, using permanent magnets integrated into the copper block, a design German researchers considered impossible to achieve with the required magnetic field strength. General Lieutenant Wolfgang Martini, head of Luftwaffe Signals Intelligence and a trained engineer, arrived at the crash site. He immediately recognized the significance. The equipment was far too compact and the antenna far too small for operation at frequencies Germans considered practical. This was sophisticated working technology. Transported to Telefunken's Berlin laboratories, Professor Brandt and his team worked through the night, meticulously measuring and documenting the device. X-ray examination revealed the precise internal structure and components, confirming the complexity of the engineering. On February 4, Brandt's team powered the magnetron, inferring the operating parameters from their examination. Based on their decades of experience, they expected maybe 100 watts of output. The result was staggering. The magnetron produced approximately 10 kilowatts of pulsed power at precisely 3 gigahertz. The output was stable, repeatable, and far exceeded what German theory predicted was possible. Brandt wrote in his initial report that the British had achieved in practice what German mathematics declared impossible. The tiny device generated more microwave power than German laboratory equipment filling entire rooms could produce, and did so with superior efficiency. The implications were immediate and devastating to the German war effort.
The 9-centimeter wavelength allowed for a small antenna to provide resolution fine enough to detect individual buildings from high altitude. This meant the British could create precision ground mapping radar, capable of showing cities, rivers, and coastlines with clarity impossible at the longer wavelengths Germany used. German radar development had entirely dismissed centimetric wavelengths as impractical because they could not generate sufficient power. The British, in fact, had solved this problem 3 years earlier. John Randall and Harry Boot at Birmingham University had produced the first working prototype in February 1940. By late 1940, General Electric Company engineers had increased the output to 10 kilowatts. By 1941, production magnetrons were achieving over 100 kilowatts in pulsed operation. At a highly classified conference on February 5 in Berlin, Brandt presented his findings. The mood was somber. The British cavity magnetron represented not an incremental advance, but a fundamental technological breakthrough that Germany had missed entirely. Germany had abandoned high-power microwave development because mathematical models indicated it was not feasible within wartime production deadlines, channeling limited resources into improving existing, proven systems. The British had not just solved the engineering challenge, they had been operating the technology for months, possibly years. The conference participants began connecting seemingly disparate intelligence reports. Reports from U-boat commanders described being surprised by aircraft attacks in conditions where detection should have been impossible. Luftwaffe bomber crews reported being intercepted by British night fighters with suspicious frequency. It became clear that the British had not just developed one system, but an entire family of applications based on the magnetron. The H-2S was for ground mapping. ASV Mark III radar, also centimetric, was used by Coastal Command to detect surfaced U-boats at night. The narrow beam width of this centimetric radar rendered German Medox radar detectors useless, leading to a catastrophic spike in U-boat losses. Additionally, British night fighters were using centimetric AI Mark VIII radar, which was far superior to Germany's Liechtenstein systems, whose large antennae created significant aerodynamic drag. The captured magnetron was designated the Rotterdam Gerat, Rotterdam device. An immediate working group, the Arbeitsgemeinschaft Rotterdam, AGR, was formed with a threefold mandate: understand the magnetron's performance, develop countermeasures, and begin German development of an equivalent technology. On March 1, 1943, the situation took a bizarre turn. During a major RAF raid on Berlin, bombs struck Telefunken's facility, destroying the only complete captured magnetron. The loss was devastating. Yet, in an extraordinary stroke of irony, that same raid provided a replacement. Another H-2S-equipped bomber, a Handley Page Halifax, was shot down that night in the Netherlands, providing a second, largely intact unit. This confirmed the devices were standard production hardware, not hand-built prototypes, implying substantial British manufacturing capacity. The copying process resulting in the German LMS-101 magnetron revealed the layer upon layer of British engineering sophistication that severely challenged German manufacturing. The cavity dimensions required extraordinary precision, with tolerances of 0.02 millimeters or better. German machine shops accustomed to much looser tolerances were not equipped for this scale of precision work. The oxide-coated cathodes required materials and processes that the German chemical industry had not perfected. The crucial permanent magnets required cobalt, a strategic material Germany had in critically limited supply, a supply that had been cut off when Germany invaded the USSR. Diverting the scarce cobalt for magnetrons meant reducing its allocation for other military necessities, such as aircraft turbine blades and cutting tools. Dr. Otto Hockenberg, an engineer assigned to the AGR, later recalled the psychological impact. They were examining equipment that proved British engineers had solved problems they had declared unsolvable. It was production hardware, suggesting the British were already on their third or fourth generation of development, while Germany was attempting to start its first under intense pressure. Through interrogations of the captured aircrew, German intelligence learned the system was called H-2S, and that Bomber Command was fitting it to the entire Pathfinder force. This suggested British production capacity was sufficient for manufacturing these devices in the hundreds, possibly thousands. Meanwhile, the AGR pursued countermeasures, quickly developing the FUG-350 Knollnox, or KNOS, a simple receiver tuned to 9-centimeter wavelengths that night fighters could use to home in on the H-2S emissions. KNOS was a successful countermeasure, but it was fundamentally a reactive technology, entirely dependent on the British operating their radar. The final disparity was not just technological but industrial. Germany could ultimately understand and even manufacture copies of the technology. Technical analysis confirmed the German LMS-101 magnetrons were functionally equivalent to the British originals, but Germany lacked the industrial base to produce the technology at scale while simultaneously dealing with Allied bombing and resource shortages. Britain was producing thousands of magnetrons monthly. Germany production peaked at perhaps only 20 units monthly. The gap was not in scientific knowledge, but in industrial capacity, strategic prioritization, and resource allocation. By the summer of 1943, the full scope of Allied centimetric radar deployment was apparent. H-2S enabled precision bombing. ASV Mark III forced U-boats into temporary withdrawal from the North Atlantic, and AI Mark VIII decimated German bomber forces, effectively ending the German strategic bombing campaign. In examining the captured magnetron, German scientists realized they had lost a technological race they had not even known they were running. The gap was not merely a historical curiosity, it was a strategic fact that influenced military operations throughout the war's final years, contributing to the Allied victory in measurable ways across multiple theaters. The tiny copper cylinder was evidence that warfare had entered a new domain where the industrial capacity to manufacture advanced electronics at scale was as vital as armies in the field.